approximation algorithm. Yeah, so the title of the talk is Our Graph Neural Networks, Optimal Approximation Algorithms. And this is some work with Eric Liu at Harvard, Nikolaos Corralius, who's a postdoc in Stephanie's lab, and Jessica Shu, who I think she was just recently working at Reverie Labs, and Stephanie Agelka, who is a professor at MIT and TUM Munich. So what do we do? So perhaps we should start with what computers cannot do. Right. So what can computers not do? They cannot solve like NP hard problems. So like really hard combinatorial problems. Because computing is difficult. And if you have a combinatorial search space, things become really hard. So what are examples of this? Think about like you're a traveling salesman problem. You're a salesman. You're trying to move across American cities. And you want to be able to minimize the amount of fuel that you use. So you got to like go on a minimum distance tour of America. And that's really hard. You can take like boolean satisfiability. The boolean satisfiability is like, oh, like I have basically a bunch of variables and a bunch of constraints over these variables. And it is very hard to satisfy all the constraints because that is difficult, or even the maximum number of constraints. So, these things are hard because they're combinatorial. And also things like games, like imagine like Sudoku or Go or chess, like these things are hard. But this is a little different because this is the hardness of games. Which is not NP, it's actually PPAD, but still hard. And yeah, so optimization and searches are hard, and they have applications everywhere. You might want to know about the traveling salesman problem because of like routing. You might want to know about Boolean satisfiability because of program verification, let's say, or anything that uses a SAT solver. And you might want to know about games because, of AI. So what happens if we have an arbitrarily powerful computer? Well, then we would be able to, route essentially as well as we can. So we would have vehicle routing. You could route robots in warehouses. You can do all things like that. And also computation is just very important. People can clearly kind of see that. We do a lot of matrix multiplications. And so, there's this recent like alpha tensor for, multiplying matrices faster. And finally, there's of course like recently, like they shoved an LLM onto some sort of a geometry solver, which is kind of like a SAT solver if you think about it. And they were able to get some Olympiad level AI systems for geometry. So that's like pretty cool stuff. And what we're going to talk about is sort of a like theoretical and technical underpinning, and also experimental underpinning for how to understand things like this. That's what we aim for. And you might as well hear it from the horse's mouth, I guess. So Bengio, Lodi, and Provost at the Polytechnique, Mila, they wrote some survey about sort of like the general take on the field in 2017. And so the basic sort of philosophy is that no algorithm is evaluated on the worst case inputs. And the question is it possible to learn the distribution over instances that an algorithm is presented with that enable efficient computation? And so now there's, of course, a problem. How do you feed computation or instances of computation into a neural network? Does that make sense? Okay, well, I guess it does. So our running example is going to be max cut. So what is max cut? Given a graph, here the graph is, and imagine you don't know that on one side it's red and on the other side it is, I guess, bluish green. Given a graph, partition the nodes into two disjoint sets that maximize the number of edges in between the two sets of nodes. Now you can imagine that this problem is not that easy, because what you should have in mind is more like maybe the graph here on the far right. It's huge. And so how am I supposed to partition the graph into two sets of nodes that maximizes the number of edges in between the two sets of nodes? This is really hard. Okay. So I hope you can, intuitively at least feel like, wow, this is a fundamental NP-hard problem. It's one of CARP's 21 problems. And these are the sort of things that you can kind of begin to think about and ask, like, okay, like, how well does a neural network do at computing the largest cut of a graph or satisfying as many SAT instances as possible? Things like that, right? So this brings us into the question of how do you feed a graph into a neural network? So basically every computation you come across, whether it was routing or whether it was Boolean SAT or, really anything you care about, there's always usually a graph, the graph of variables and constraints. And so the question becomes very quickly, how do I feed a graph into a neural network? Here's maybe like, your undergrad take, which is actually maybe not that bad. So you go like, oh, I have a graph. Now I have an adjacency matrix. So that's a matrix. I got to have a matrix somewhere. I got to, I have to have a representation. And so maybe I feed my giant adjacency matrix or my max cut into some gigantic transformer, some sequence model. And then maybe my NP hardness is solved, and you would probably submit that for your final project and it would do absolutely terrible. And the reason is quite simple. It's because actually the inductive bias of these networks matter. If you throw a completely arbitrary data format into an architecture that is not built for it, it is going to do terribly because it has no reason to do well, right? So this brings us to the topic of graph neural networks. Is there a question? No? Okay. Yeah, so this brings us to the topic of graph neural networks. So what is a graph neural network? It's a neural network that is designed specifically to process graphs. And what challenge does a graph pose? A challenge, for example, is that you should only care about the structure of your neighbors, but not exactly where they are. Like if I relabeled here on this graph the neighbors of X, the node X, as Y, Z, and W, it should not matter if I sort of permute Y, Z, and W. Like they're all the same thing. You know what I mean? So it needs to be like kind of permutation invariant. So that's kind of the key point behind a graph neural network. And I'm going to walk through exactly how it works. So we call these message passing GNNs, and I did not come up with this. This is, maybe like 2010 or something. It's got like 50,000 citations. It's like a very famous thing. So the basic idea is each node in a graph is represented by a vector. Okay, so that's got to be represented by something. And the GNN is a function of the graph, G, and its embeddings, V1 through Vn. So each embedding is a vector, right? Now, embeddings are updated as they pass through the layers of the graph neural network, right? So I want to kind of change these vectors as they pass through a neural network until, they do something meaningful. Okay. And in the end, like usually you think of this as being some sort of maybe like graph classification task. Like each node is like on a social network and you want to figure out whether everybody's a Democrat or Republican or something like that. And in the end, like maybe, finally you get some vector and the vector points all in the same direction for all the Democrats and in a completely different direction for all the Republicans. And this way you can, just see like, where they are. And so then you can figure out whether somebody is a, class 1 or class 0, something like that. Okay. So, yeah. So how do you deal with how do you update these vectors as they pass through the neural network? Well, for the node X, what it is going to see is it's going to see some messages passed to it. If you guys have heard of belief propagation or approximate message passing, this is exactly the same thing. So what happens? I am node X, and node Y sends me its vector. So now I know about its vector, right? And node Z sends me its vector. So now I know about node Z. Node W sends me its vector. So I know about node W. And now what do? Well, I gotta like apply some sort of function to it. So I'm just describing to you what a GNN does, right? I'm not yet telling you why it does anything meaningful, right? So it aggregates all of these vectors, Vy, Vx, Vz, and Vw. Okay. And the way it aggregates it is it has to apply some sort of permutation invariant function. So for example, it might take the average of the vectors. So why is this a good idea? Because if I applied some function of Vy, Vx, Vz, Vw that was not permutation invariant, then suddenly like where W and Z are and the order in which they appear just matters. And I don't want that. So like an average is a good idea. So, it could have been element-wise max. That also works. But the key is that it has to be, you have to be able to permute the neighbors and it should not matter. So imagine taking an average. So here we have taken an average. And then what we do is we feed this averaged vector or maxed vector, whatever you want it to be, into some sort of feed-forward neural network, which is basically a piece of magic, and it transforms your VX aggregated into your VX new. Okay, so that's essentially one layer of a graph neural network. I hope that makes some level of sense. Yeah. So basically, this update happens simultaneously for every node in the graph with the same nonlinearities and weights. So every single node in the graph does the following thing. It passes its message, which is its vector, which is also its embedding. These are all just, words that mean the same thing. They pass it to their neighbors, and everybody aggregates their neighbor information or their neighboring embeddings and applies some horrible complicated function and updates their own embedding. And they do this over and over and over again, layer by layer. Okay.
Are
So
the W scalars? Are the W scalars?
Are the W's, no, the W's are matrices.
Matrices. Okay.
Yeah, they're matrices. So it's this is like, so yeah, so these are like
Call them weights.
layer perceptrons. Yeah.
And the sigma is
A
mapping.
nonlinearity. Yeah.
Nonlinear map. Okay.
Yeah, it's a nonlinear map. So think ReLU, and the W's are just matrices. Yeah. So maybe D by D matrices for embeddings of dimension D. Yeah, something like that. Cool. Any other questions? No, great. Okay, so here's how message passing works, as I just kind of like said and gesticulated at. Basically, you start with some input graph, which in our case is our favorite XYZW graph. And what we do is at every layer, we take this process. We pass messages to all of our neighbors. So Y receives messages from X, X receives messages from Y, Z, and W, Z receives messages from X, and W receives messages from X, right? And what you do is you just aggregate all your neighboring embeddings and you apply some multi-layer perceptron. And you do this layer by layer for, I don't know, some number of layers. Pick your favorite number of layers. And in the end, you get out some output embeddings that I guess we'll also call VX, VY, VW, VZ. And what do we do with these output embeddings? Well, I mean, you got to like process them in some way. And so for your Democrat and Republican example, you probably take VX and you go like, okay, what is its like maybe first coordinate or something like that to determine whether it is a Democrat or Republican. And for max cut, I guess you can also do the same thing. You can just go like, oh, what is its like first coordinate? Is it closer to 1 or closer to -1? Is it very positive or very negative? To figure out whether it's maybe on one side of the cut versus the other side of the cut. And that's basically what you do. Now, how do you learn? Well, you have to have a loss function. For max cut, it's you got to think of a loss function for your cut. So how do you turn these vectors into some sort of loss function? And we're going to talk about that, pretty soon. So all of these vectors are going to have to be passed through some loss. And the loss is going to be a scalar. So then you can take a derivative and you can backpropagate the gradients to update all those W's with respect to the learnable parameters, which are all the W's, right? So there's a set of W's for every single layer, right? And the key is that, yeah, so the key is that you have data like, say, many, many different graphs. So I throw in a huge number of graphs, right? Because I want to learn how to perform like a computation across many, many different graphs. And I want to be able to, learn the distribution over instances. And so I need many, many graphs. I throw them into my neural network and it updates all of these learnable parameters via stochastic gradient descent by batching the data. Okay. And for our examples, there's no, the loss is just a function of the output because it's just some type of optimization. It is in fact, it has nothing to do with like classification, which is this sort of, Democrats and Republican example I keep giving. But yeah, so the loss is going to be a function of the output alone. Okay, and the data is going to be graphs. All right, so does that make sense? Like we have a bunch of different graphs and we want to find like say the max cut. Okay. Okay, great. So Okay, yeah. So basically that's what a graph neural network is. And graph neural networks are, they're kind of used in a lot of places. The basic point is that there are a lot of graphs. They happen, for like, in material science and protein folding, you just have to have a graph because there's a molecule, and a molecule is a graph. You have genes and, software and social networks and, anything you can think of. And I would strongly recommend you guys look at this surveys by a bunch of people. And they would probably really want you to read those surveys, and they're pretty good. So I learned a lot of stuff from them. Cool. Okay. So what does this have to do with approximation and approximation of NP-hard problems? So key insight, it is substantially easier to approximately solve an NP-hard optimization problem than it is to solve it exactly. So for MaxCut, for example, there's a famous like 88% approximation algorithm, so 0.88 approximation to the largest cut that was discovered like maybe 40 years ago at this point. And yeah, so it's way easier to approximately solve it to some reasonable constant factor approximation than it is to actually solve the problem. Okay. So, and the key idea is that, semi-definite programming, I hope you guys have, at least kind of heard of this term before. It's used in like matrix completion and kernel methods and things like that, and also approximation algorithms, and also like in like control theory and, finding a Lyapunov function, things like that. So it's like used everywhere. But semi-definite programming is a very powerful tool. It is polynomial time solvable via like either ellipsoid or primal dual interior point methods, whatever, pick your favorite convex solver. And the point is that if you want to maximize some matrix X over a linear form, like C inner product X, subject to some linear constraints. Here, these inner products are Frobenius inner products. So they're just like you take a matrix and you pretend it's a vector and you just take an inner product. That's it. That's all I'm saying, right? So yeah, subject to linear constraints like AI of X is equal to BI. And then finally, up till this point, I've described a linear program, but you can also constrain that X is positive semi-definite. So positive semi-definite is very important because this is what kind of gives it its magic. It is much more powerful than a linear program. So a linear program does not get any approximation ratio for, MaxCut, for example. And so yeah, this is a thing. This is a tool. So how do you use the tool? Okay. So this is actually a very old story, but I'm gonna tell it anyway because the point is to tell old stories. Yeah. So yeah. The object that we're optimizing over, these linear forms, this linear polytope subject to being in the cone of the positive semi-definite matrices is called a spectrahedron. And you can kind of visualize it. It's a cone intersecting a bunch of planes. It kind of looks like this object on the right. And you can see that it's convex. Between any 2 points, you put a line there, it's still inside this spectrahedron. So that's why you can efficiently optimize over it. And now what does this have to do with combinatorial optimization and approximation algorithms? Well, look at MaxCut. MaxCut is the following integer program. You maximize over the sum of the edges in the graph of some quadratic program, 1 minus xi times xj over 2. And you subject to the fact that xi is in minus 1, 1. Okay? Right? So hopefully you can kind of see why this is the MaxCut of a graph. If xi is 1 or minus 1, it is on one side or the other side of a graph cut. And yeah, that's if you can solve this problem exactly, then you have solved MaxCut and quadratic programming and NP-hardness, and you're really, really happy. But of course, it is hard to do this. So quadratic programming is in general hard. Quadratic integer programming is hard. So yeah. Now, what is the idea of semi-definite programming? It's called convex relaxation. You replace the xi times xj term with an element of a matrix, X, which you call xij, and you, of course, constrain X to be positive semi-definite, the whole matrix. And you replace the constraint xi squared equals 1 of the integer program with the main diagonal element xii equal to 1 for all vertices in the graph. Okay, so this is just a very, very old idea. And it's just a way of, it's a recipe for translating integer programs into their convex relaxation. And so you can see this convex relaxation is kind of related to this original integer program. And there's a sense in which there was no real reason in which you had to do this. This was just sort of a mathematician's guess. And this was their guess. They were like, this seems very well motivated because now my horrible problem, I have constructed a completely different problem. And this completely different problem looks vaguely like the original problem. Okay. And if you wrote it down as a semi-definite program exactly, you'd be minimizing some a inner product x. So there's maybe like a 1/2 or 1/4 in front of it. Please ignore it. And it's minimized because there's a negative sign, but it doesn't matter. For some adjacency matrix A, subject to the linear constraint that xii is equal to 1 and that x is positive semi-definite. So this is the semi-definite program for max cut. And hopefully, I don't know, I feel like it depends on my audience. I feel like for TCS audiences, usually people have seen this, and for like machine learning audiences, this is usually rather new. Okay, so but that's the basic this is the basic setup. Now, how do you solve this semi-definite program? Okay, so here's there are actually many ways to do this, but here's a sort of a well-motivated idea. You represent each xi with a vector vi. So now I have a bunch of vectors. Imagine a bunch of unit vectors, a unit vector for every single node in the graph. And then I update these vectors via some sort of gradient iteration. And so what do? I go like, hey, how do I update my vector? I take my neighboring vectors. I kind of like, sort of like, I like kind of like add them all together. And I apply a negative sign times some sort of step size. And then I move in that direction. And then I normalize again so that my vector is once again a unit vector. Okay, so this is just like it's called like a Beer-Montero. It's like a very good way to solve this semi-definite program. And the point is that eventually I'm going to be able to represent every single node as a vector, and that this vector will be the vector in the Cholesky decomposition of the positive semi-definite matrix X. So you can actually, in fact, if you want, just completely forget this positive semi-definite matrix. It's almost like a bit of a red herring. And just think about these vectors. You go like, let's say we are all vectors on a graph, and we want to compute the max cut. What would be a good algorithm? So algorithmically, I would take all of my neighbors, like say it's Steve and Sergey and whatever, and I would like take all their vectors. And what should I do with all these vectors? I should point in the opposite direction of these vectors, right? Because if it were the greedy algorithm, they would maybe be like +1s or -1s or whatever. So if they were all +1s, I should be -1. You see what I mean? Because we want to maximize the cut of the graph. So if they're vectors, I mean, the natural generalization is that I should point in the opposite direction. And we are all on the unit sphere. And so I just kind of want to like move away from them and then project back onto the unit sphere. This would be projected gradient descent. I hope this like, at least at an intuitive level, this makes sense. Proving that this works actually takes quite a bit of effort. And it's something you can look, it's like a really, really long line of research. But the point I'm trying to make is that, oh yeah, so actually one more thing, how do you relate these vectors back to your max cut? You should, in the end, when you finally output all these vectors, you should take their inner product with some random hyperplane, like say it's the first coordinate, and you just look at your first coordinate and go like, oh, is it positive or negative? If it's positive, just say I'm +1. If it's negative, just say I'm -1. So you take the inner product of all these vectors with a random hyperplane H and let xi equal the sign of H inner product vi. It's like a classifier if you want to think about it that way. So yeah, that's the Gomans-Williamson max cut algorithm. And this always outputs an 88% approximation to the largest cut in a graph. And it is a story 40 years old. But the algorithm is actually a story that's 20 years old, and its analysis is more like 10 years old. So it's that's sort of the history of this sort of thing. Okay, so this is really old. And hopefully you can kind of like see already. Actually, I'm going to go back to this whole vectors on a sphere thing. that the process I just described, take all my neighboring vectors, add them together, and kind of move in the opposite direction. This is something that a graph neural network would find very easy to do. Like a graph neural network literally takes all of its neighboring vectors, averages them, so basically adds them all together, and then applies some function to it, some big, horrible, complicated function. And it's like a stack of matrices and nonlinearities. It is very easy for it to implement something like move in the opposite direction and normalize. It is really, really easy. And so graph neural networks can actually just kind of do this. It can like implement this algorithm. And so if you use this insight, it's a mathematical insight, but it's also like an implementational insight. Like you can actually get this to work. You can just code it up, a standard graph neural network with maybe like, slightly different nonlinearities so that it is able to perform this projection onto the unit sphere. And you can ask it to perform this task, like arrange vectors on a unit sphere. Actually, I'm just going to go back to this unit sphere because this is actually the whole point. You can ask it to arrange vectors on a unit sphere such that it looks like the solution to a quadratic program or even a, like a cubic program like SAT, right? So you have to be able to formulate SAT correctly or, any other type of problem correctly. But that's the basic point, where you can take combinatorial optimization, which is really hard. You can just formulate it as a problem about arranging vectors on a sphere, which is a story that's like, half a century old. And you can ask a neural network to do the same thing and see how well it does and prove some theorems about it. So the basic idea is that this sort of thing holds at immense generality. It's not just max cut. So think about like a max constraint satisfaction. So a constraint satisfaction problem is given a set of constraints over variables, satisfy as many constraints as possible. So think about SAT. I have a bunch of like literals and clauses. I want to satisfy as many as possible. That's Boolean SAT. Max cut was also the same thing. The constraint was one and minus one is like is the reward is +1. And I want to be on different sides of the cut. And this also includes games like Sudoku and etc. But these are max constraint satisfaction problems, and constraint satisfaction problems are everywhere. And there is a sense in which you can actually characterize how well an algorithm can realistically do at satisfying constraints. It is, like vaguely, it's called like the unique games conjecture, and it's about a very specific type of constraint satisfaction problem. But the conjecture itself can be sort of boiled down to there's a semidefinite program that achieves the optimal approximation ratio for any max CSP. And it is a very famous conjecture in theoretical computer science. And yeah, it somewhat divides the community as to whether it is true or not, but it is probably true. And even if it is not true, it would be an enormous breakthrough. Like you would have to come up with a better than 88% approximation for max cut. And essentially all of those approximation ratios are 40 to 50 years old. So if you were able to disprove this, you would be extremely famous and you would have a really nice job. And so it is, that's sort of the state of affairs. And so what we were able to prove is a representational theorem. There is a graph neural network that represents the algorithm for solving the unique games optimal semidefinite program for any max CSP. So for any max CSP, there is this whole picture of arranging vectors on a sphere. And there is a graph neural network that represents the algorithm for computing the optimal arrangement of vectors. And that is something that we prove in our paper. And furthermore, this GNN is pack learnable. So given a polynomial number of samples, it will in fact learn this particular SDP. But this is polynomial number of samples. It's not polynomial time, right? So gradient descent might not actually be able to learn this, given a polynomial number of graphs, right? So it's pack learnable. It's sample complexity. So that is actually what we did theoretically. And then we implemented it. Now I'm going to show you what we did to implement it. Are there any questions at this point? No. Okay, that's shocking. Okay, cool. So we implement our theorem via this OptGNN architecture, and we deploy it on benchmarks in the neural combinatorial optimization literature for max cut, min vertex cover, and max 3 sat. And we just see how well it does. We just like took a bunch of graphs, we shoved it into a GNN, and we saw how well it could compute. Okay, so we compare against like say like Groby. Groby and CVXPy are like standard solvers for NP hard problems, and I guess you can call them state of the art solvers. And greedy is just greedy is everyone knows what greedy is. So you take a bunch of like standard graph data sets that are like I don't know like Erdős-Renyi and Barabasi Albert or whatever. These are like synthetic data sets, or you can take data sets from the torch geometric library, and you just compute the max cut, and you train OptGNN on it, and you train. Oh, you don't need to train. You just deploy greedy and Groby on it for like say 0.1 seconds or a single second, and you see how well they compare. So to be clear, so this OptGNN is maybe like imagine like 16 layers with vectors of like dimension 32. It is like pretty small. So it executes in about like 2 milliseconds. Okay. So Groby for 1 second is it's a lot compared to 2 milliseconds. And in about 2 milliseconds, it essentially it will absolutely kill greedy, which is expected. And it is within like about a percentage, like 1% of performance of Groby across the board and across every single data set. So this might just be because we chose some pretty easy data sets. They're not small. They're maybe like 4,000 edges. That's the sort of like size you should think of. But these are like this is sort of the first batch of experiments. Then we went on to vertex cover. So for vertex cover, here the smaller numbers are better. This is the ratio to the smallest vertex cover. And you might be asking like, Morris, why did you report all the numbers in a different fashion in every table? It's because you have to compare against every other table that everybody else put down. And their conventions for every single data set are different. So you have to make it so that other people can read it and understand like, oh, how this compares to my table. Anyways, so this is a comparison against essentially the state-of-the-art unsupervised methods. So think reinforcement learning. And these are like like run CSP, meta EGN, Erdős-GNN, CMP, whatever these are. And we run them against all of them, and we beat them all actually. And we are essentially able to like virtually tie Groby up to like 0.5 seconds or a single second. And again, we run in like millisecond, like 1 to 2 milliseconds. It's again like about 16 layers, right? So this is how well we do on like this forced RB dataset, which is a generator for hard vertex cover problems. We also deploy it on 3-sat just to see how well it does. So this is more of a very experimental thing to see how well it does. And indeed, you can also write down a semi-definite program for 3-sat. It's actually never been implemented before, really. And so we implement it and we see how well it does. And we find that, it beats other neural baselines. It beats AutoGrad on the same loss that we train on. Because again, you can take our loss and you can deploy AutoGrad on it. And we can beat that substantially. And but we do lose to like things like walksat. Walksat is really, really simple. It's just twiddle some bits, And so SAT solvers are very powerful. And to this day, I don't think there are any neural networks that are like at all competitive with SAT solvers. And so this is on random SAT instances. Okay. So yeah, so that's what this table represents. Finally, like you might be able to catch something if you're able to kind of solve a semi-definite program with a graph neural network. Something that you might be able to do is you might be able to output a dual. So if you take the output embeddings of a graph neural network, which is just a bunch of vectors, you can just kind of like compute the dual, right? So that's a primal solution, and you want to be able to compute the dual, and you look at how well the dual bounds the size of the optimum cut, right? Something like that. You have a combinatorial optimization problem. The dual tells you how big it could possibly get, right? And so here we output essentially what our duals look like. And you can see that for the SDP, the dual values are in red for max cut, and the dual values for OptGNN are in blue. Now, ours are larger which means that they are worse, right? Like, you see what I mean? Like, the bounds are looser, right? And it's also because we run in like 2 milliseconds. Whereas for the SDP solver, it takes maybe like a second to process these, right? And so like we are very fast, but it's also like very dirty and very approximate. And so we do lose some things, right? And that's just like a point that we felt was important to emphasize. That it's also like we did not actually build an SDP solver. Um, because in the end, it has to adapt to the distribution over instances. And that is actually very important. So when we run our like hyperparameter search, it is important that we run it over vectors of many different dimensions and many different layers and things like that. And so we are actually tuning to this data set. Okay, so this is also it's another dual certificate comparison. Cool. So are there any questions? Or are there no questions? Okay. Yeah. I think there might be no questions. All right.
I'm saving mine for the end, just so you know.
Okay, cool, cool, cool. So we also compared OptGNN to other GNNs. So we ran a gigantic ablation for comparing this our GNN architecture against everybody else. And so these are like graph attention networks. They're GATs, and then graph convolutional neural networks and graph isomorphism network, and then like gated GCNNs. And these are just like very canonical graph neural network architectures. And we just saw how well they can do against like, just a very basic set of like torch geometric graphs. And we see that we can beat them all. That's quite nice. And it's not exactly, it's not that surprising actually. The reason is because like these neural networks are really, really complicated. And if they don't have like some very clear inductive bias for solving this problem, they of course cannot beat a network architecture that was sort of like kind of tailored more for combinatorial optimization. So, but we do show that we in fact beat them all, and that's a very good sign. Cool. And we can also beat them all for min vertex cover. So I think like on the point of which graph neural network architecture, if you were to restrict yourself to GNNs that you would like to solve a combinatorial optimization problem with, you should probably go with the one that we designed. Cool. So also like we find that if we train on one data set and we try to evaluate on a completely different data set, then in fact, we actually do pretty well. So like, and this is probably due to the fact that it kind of looks like semi-definite programming. So if you train on one data set and you evaluate on an entirely different one, it's pretty robust. Like the performance does not just completely dissolve. So you can see here that, okay, on maybe like this Colab data set on the bottom left, if you train on Colab and you deploy on Colab, you get some, probably the best performance out of everything. And if you deploy it on other data sets, you still do pretty well. Like for this, if you deploy on IMDb binary, you still do pretty well. So like, it's very robust and it works really well. Cool. And finally, like, I think like it's an important point to emphasize. In the end, like, we build something, we ablate over a lot of models and we figure out how well it works. If you compare it against like, say, a semi-definite program, you realize that actually it works better than semi-definite programming. And that's kind of the key, right? It's like it captures semi-definite programming within its weights, but it could have learned a better algorithm, right? And that's what we see here. If you take these gset instances on MaxCut, these are maybe like 3,000 nodes and maybe like 30 to 40,000 edges. So it's actually a huge graph. And you're measuring the number of nodes you are away from the best MaxCuts ever found on these data sets. You find that the SDP is maybe 245 or 229 nodes away. But for OptGNN, it's like more like 109 or 125. So we are actually beating semi-definite programming. So this is something that we found like pretty consistently, that we can beat semi-definite programming. And if we take the loss of our architecture and we applied like gradient descent, we can also beat that particular algorithm, right? So those are important things, right? And finally, like we find that when we compare against like other state-of-the-art approaches, we like are like vaguely competitive. I think like for these really, really large graphs, on this particular this particular data set, we sort of taper off when the graphs are really, really big. And this probably has to do with the fact that we used a message passing architecture. It's very hard for these message passing architectures to do really, really well on really large instances with like large diameters. So that's what we find here. Okay. So yeah, that's I figure that was a little faster than I imagined, but that's the talk. Do you guys have any questions?